Project 3.1, the CharlieClock, by Atticus Stiplady. The purpose of this project is to create a functioning clock that is powered by an RSGC, ACES PCB, and CharliePlexing, along with many other small attachments such as a 12mm momentary push button and an RTC seen in earlier projects. As stated previously, the fundamental aspect of this project has to do with something called CharliePlexing. CharliePlexing is a technique used in electronics to control a large number of LEDs with a relatively small number of microcontroller pins. Looking at the clock in this assignment, with the inclusion of 132 LEDs, 12-hour pins, 60-minute pins, and 60-second pins, instead of being forced to utilize 133 pins to individually control each LED, 132 voltage, 1 common ground, CharliePlexing allows us to only utilize 12. Since LEDs are diodes, meaning that current can flow in only one specific direction, if a positive current was introduced to the wrong pin, no current will travel through it, keeping it off. Charles Allen, who introduced the concept of CharliePlexing, realized that in addition to the high and low output states, there was a third state called high impedance, high Z. In this high Z state, a microcontroller can monitor voltage with minimal current flow, similar to setting a pin as an input in Arduino, allowing efficient control of an LED matrix with fewer microcontroller outputs. This means that when turning on an LED with 2 wires and there's a third one in the loop, the third wire will be high impedance, while the other 2 will be voltage and ground. In order to calculate the required number of pins to power every single LED, you can use the equation n is going to equal 1 plus the square root of 1 plus 4n divided by 2, where n is the number of pins required and capital N is the number of LEDs. So if you had 15 LEDs and you wanted to know how many pins you needed, you do 15 times 4, which is 60. 60 plus 1 is 61. Square root of 61 is 7.8. Plus 1 is 8.8. Divided by 2 is 4.4. However, since 4.4 is not a full number, you need to round up, so you need 5 pins to control 15 LEDs. The equation can also be written as LEDs P2 or LEDs factorial divided by L minus 2 factorial, which equals the number of outputs. Another interesting feature about the RSGC CharlieClock has to do with the fact that an RTC is included. An RTC, real-time clock for short, is also powered through the use of an I2C bus. This video will briefly touch on what these two ideas/parts are as I go into full depth in my project 2.6.1 and 2.6.2 video found on my channel page. An RTC, real-time clock, is a specialized clock module designed to keep track of the current time and date even when the system it's connected to is powered off. It uses a small battery to maintain accurate timekeeping and is commonly used in embedded systems to ensure time consistency. RTCs are critical for applications requiring precise time tracking such as clocks, data logging, and schedule systems. The RTC is able to be connected and utilized in the construction of the clock thanks to something called the Inter-Integrated Communication, or I2C bus. I2C is a common communication protocol that allows multiple devices to communicate with a microcontroller using just 2 wires, one for data, SDA, and one for clock, SCL. It's commonly used in embedded systems to connect sensors, displays, and other peripherals due to its simplicity and efficient use of pins. Taking a look at the code included within this project, it involves a lot of concepts mentioned and discussed in other projects, but includes some new, useful ideas. The code begins, like many others, by declaring all the pins and what they are connected to. Following this, the code declares many separate things such as a struct containing the cathode and anode variables and a 2-dimensional array declaring all the pin combinations. The array is sorted by listing out every single LED combination, declaring their anode and cathode pin mode using the struct created previously. The setup function attaches interrupts for the select and add buttons, starts the wire library for communication, and sets the initial time. The loop function continuously gets the current time, displays it, and checks if the select button was pressed to trigger a time change. Functions like sell and add handle incrementing the select and add counters, while time change allows the user to change the time, updating the time components, hours, minutes, seconds, as needed. Other key functions include display, which controls the LED matrix by setting the correct pins, and get time and set time, which communicate with the RTC to load and write time values. Utility functions handle conversions between decimal and BCD formats. The BCD to DEC and vice versa are also found within other projects such as the 2.6 mini-series. The case design went through many iterations before we landed on our final idea. This case was extremely entertaining to create, and I was able to put the clock on an angle thanks to the creation of an angled plane which a sketch was created on. The PCB was another interesting aspect of this project, as the first iteration had a few small mistakes, but the second ended up working perfectly. There are some extensions to the primary clock, such as including buttons that will allow you to manually change the time, designing and creating a PCB, and including the RTC to help keep track of the time. Thank you for taking the time to watch my video on the RSGC ACES Charlie Clock.